Okay, for the relationship between acceleration and displacement, basically we know that acceleration is equals to negative omega squared x. So if I plot a graph of x against acceleration, okay, it'll be a straight line negative gradient through the origin. And then this will be the maximum amplitudes. Why? Okay, let's say this object, let's say this is 0, okay? It will move until the farthest right, okay? On the graph, it's shown like this, okay? This is peak displacement to the right. So this is called, at this point is called XO, okay? At this point, we know that acceleration is also maximum in the opposite direction. So when XO is positive, acceleration is negative, okay? So that's why you get this, okay? Acceleration max. Acceleration max. Okay? And then it goes back and then it goes to the farthest left. Same thing. Same magnitude but just different direction. Okay? That's how you get this graph. And then the gradient is just omega square. Negative omega square. Okay? You can look at it as y equals to mx plus c. A equals to negative omega square x. So the gradient is equals to negative omega square. C is 0. That's all. And then this is the condition. Simple harmonic motion only occurs when acceleration is directly proportional and always directed towards equilibrium. Okay. And then this one is just connecting spring and simple harmonic motion. Okay. So we know that, let's say I have a spring. When I pull it downwards, there's a force acting upwards. So F equals to negative kx. Because the force is in opposite direction to displacement. Okay? So negative kx. And we also have F equals to ma. So A equals to negative k over mx. Okay? As you can see here, k, spring constant, m, mass, also constant. Okay? So it's also the same as A equals to negative omega square x. So for this both, A is directly proportional to displacement, and also A is negative, or you can say opposite of x. Okay, both are the same. And if you want to compare, so for spring, omega square equals to k over m. Okay, and we know that omega is what? 2 pi over t. For one complete oscillation, it's 2 pi over t. So you can get 2 pi over t squared equals to k over m. Rearrange everything. 2 pi over t equals to third k over m. T equals to 2 pi third m over k. So for a spring, okay, moving up and down with a object mass of m and a spring constant of k, the period of one complete oscillation which is moving up and down is equals to the formula 2 pi third m over k. Okay, so this one is for spring with object of mass m and spring constant k. Okay, this is the first formula. Okay, period of oscillation of a mass connected to the spring. Next one, equation for velocity. We learned that x equals to x naught sine omega t, v equals to x naught omega cos omega t. Okay, from these two, let's say I rearranged it. Sine omega t equals to x over x naught, cos omega t equals to v over x naught omega. Okay, and according to trigo formula, okay, x square cos square equals to 1, so you can substitute everything. Okay, then you can take everything out. Okay, this is your equation of velocity. Okay, okay, so this one is to calculate velocity at certain time t. This one is calculate velocity at certain displacement. Okay, now for the energy, we'll be looking at kinetic energy and potential energy. Okay, let's say